All right, so let's continue on with our discussion of these carboxylic acid derivatives. And in particular, the reactions that we're going to see. This is going to be a lecture that's going to be sort of a general overview of the type of reactions that we can expect. And then we'll talk specifics with each of those different derivatives. Okay, so first thing, activity of these different carboxylic acids. They all have a different sort of degree of reactivity, how easy it is to get them to react. The most reactive are going to be those acyl chlorides. Followed closely, also pretty freaking reactive, are the acid anhydrides. Esters can be lumped into the same sort of category as carboxylic acids, and those are next in line. So we're going to kind of think about them as being very similar. They obviously both have that oxygen bound to the carbonyl carbon. And then the least reactive are the amides. Okay, so there's four different factors that come into play here. When we're talking about reactivity, what we're really talking about is the electrophilicity of these carbonyl carbons, right? We learned in aldehyde and ketone lecture that carbonyl carbons are electrophilic because you have the oxygen pulling electron density away. Here with these carboxylic acid derivatives, you have another heteroatom bound to that carbonyl carbon, sort of doing even more, right? So making it even more electrophilic, okay? This is either by induction or resonance. Okay, induction is sort of related to electronegativity. Resonance, we obviously know you can sort of draw the resonance contributors. Other factors that will come into play would be sterics. So if you have a big bulky group surrounding that carbonyl carbon, that will also make a difference. And then lastly is the quality of the leaving group. Okay, so very different from the aldehydes and ketones section. What we're going to see is that these heteroatoms, so in the case of an acyl chloride, that's the chlorine. In the case of an acid anhydride, that's that guy right there. These are going to play the role of a leaving group, okay, in these reactions. So for example, the chloride ion, we know, is a fantastic leaving group because it's a completely crap base. In this case, with the acid anhydrides, what would be our leaving group? Would be a carboxylate ion, right? That's also a very weak base, good leaving group. We sort of go to the extreme down here, our leaving group would be the amide ion. This is a strong base, so that's a much worse leaving group. So that's also going to influence the reactivity of these different things, or rather explain the trend that's illustrated here, is this idea of the quality of that leaving group. I will just say that although we would say that this is a strong base and not a great leaving group, we will still see reactions where it plays the role of a leaving group. It's just important to know that those are slow reactions, or reactions that favor the reactants rather than the products. Nonetheless, we will see mechanisms where that's the case. And again, mechanisms are going to be a huge part of this chapter. The other thing that we're going to see, and like sort of keep in mind, we're going to see over and over again, is because of this reactivity trend, it's really easy to convert something that's more reactive into something that's less reactive. So we're going to see reactions that convert acyl chlorides to all of those different functional groups. Likewise, for acid anhydrides, it's going to be very easy to convert those into something that's less reactive, okay? Because really what we mean by reactivity is sort of free energy favorability. So if you're on the more reactive end, that means in terms of your free energy diagram, you are sitting at a higher point than something that's less reactive. And this is, of course, a free energy diagram that illustrates a reaction that favors the formation of products. That's not to say that it's impossible or we won't see reactions that go, say, the other direction. It just means that those reactions are either less favorable in the sense that they don't favor the products. So you're going to have to do some sort of tricky, have an excess of one particular reagent in order to help drive it in the directions that you want. They're also going to need to be catalyzed by heat or strong acid or something like that. So I'm not saying that we can't go in the other direction. It's just that it's really easy and really favorable to go from something more reactive to less reactive. But real quick before I move on, That is largely the name of the game this chapter, is transforming one of these carboxylic acid derivatives into another one of these carboxylic acid derivatives. And it's going to seem like a lot of reactions, but we're going to use the same pattern over and over and over again. Okay, so first of all, the acyl chlorides, why are they one of the most reactive groups? Well, you have this electrophilic carbonyl carbon. What makes a good electrophile is it's electron deficient. And so by putting a chlorine there, carbon, it electronegativity, hoard even more electron density, making that carbonyl carbon even more electron poor. Halogens do have lone pairs of electrons, and we might think that that might sort of decrease the electrophilicity because they can donate a pair of electrons to that. However, halogens really don't participate in resonance, use their electron pairs to participate in resonance like this very often. We kind of saw this same thing with regard to the benzene derivatives and their reactivity. The dominant feature with halogens is this idea of induction. And this is in contrast to what is the least reactive group, and that is the nitrogen heteroatom on our carbonyl carbon. First of all, it's less electronegative than chlorine and oxygen, so it doesn't have that same ability to pull electron density onto itself through electronegativity. The other thing is that this does have this major resonance contributor, right, where that pair of electrons on that nitrogen can be donated to that carbonyl carbon, sort of decreasing its electrophilicity, increasing the amount of electron density on there. In the case of nitrogen or an amide, this is a fairly significant resonance contributor. So that's sort of, it helps explain why you have the decreased reactivity of an amide relative to an acyl chloride. And all of the oxygen derivatives, rather the carboxylic acid derivatives that have oxygen sort of sits in the middle, right? Oxygen is negative, so that's going to help with the induction side of things, increasing electrophilicity, but it also has those electrons that it can donate through resonance, so decreasing electrophilicity. So there's going to be like that balance there, which is why it fits in the middle. Okay, so again, sort of talked about this, but let's make it super duper explicit. The big difference between these reactions and what we learned last chapter is this idea of the heteroatom acting as a leaving group, okay? Ketones and aldehydes and carboxylic acids and all those derivatives, they're obviously very similar because they share that structural feature of the carbonyl group, right? Both have this carbonyl group. However, we want to keep them in different places in our mind, right? There's a reason why we studied aldehydes and ketones in one chapter, and we're going to lump all of our carboxylic acids together in another chapter. And that is this idea of a leaving group. In all of these cases, in all of our carboxylic acid derivatives, you have a functional group that can play the role of a leaving group. So these are always a heteroatom, some sort of a chlorine, some sort of an oxygen, or some sort of a nitrogen. Again, these aren't great leaving groups, but they can play the role of a leaving group, okay? Versus an aldehyde and ketone, right? So for a ketone, you would have to kick off a carbanion to be as a leaving group. That's literally the strongest base that you can possibly get. Carbanion is not going to ever be used as a leaving group. Likewise, with an aldehyde, you have this hydride ion that you would have to kick off as a leaving group. Also just not going to happen, right? So all of our reactions around aldehydes and ketones, we saw nucleophilic attack of that carbonyl carbon, but then that was kind of it. We just protonated the negatively charged oxygen that was generated. Here, we're going to see these heteroatoms function as a leaving group. And so what happens is you're going to have what's called a nucleophilic acyl substitution reaction, right? So substitution, it's not just an addition. You're actually swapping out whatever that heteroatom was for a new nucleophile, right? So substituting those two functional groups. And then also, again, the key feature here is that we have that heteroatom acting as a leaving group. These are all going to follow the same general reaction mechanism. Again, we're going to see a lot of different reactions in this chapter, but they're all going to follow sort of the same logic. You have a nucleophile that's attacking, what do you think our well, I just gave it away. Our electrophilic site is going to be, that's going to be that carbonyl carbon. This is what's going to form what we call, so everybody just convince yourself that this is indeed what we get. This is what we call the tetrahedral intermediate. Okay, why is it called a tetrahedral intermediate? Well, simply because we went from having an sp2 hybridized trigonal planar carbon to now an sp3 hybridized tetrahedral carbon. Okay. The reason why the tetrahedral intermediate is important is because once you form your tetrahedral intermediate, you're always going to ask yourselves the same question, which is, do I have a leaving group? We formed our tetrahedral intermediate with aldehydes and ketones, but we didn't have any sort of a leaving group. So it was kind of stuck there, and we just went ahead and protonated that oxygen as our last step, right? In this case, we're going to look at our tetrahedral intermediate and ask ourselves, do we have a good leaving group? And if we do, that leaving group's going to get kicked off. But that impetus comes from the pair of electrons on the oxygen wanting to come back down. Okay, so the second step is going to be that pair of electrons comes back down and kicks off the leaving group. The bottom line is that this alkoxide ion that's formed in our intermediate is not terribly stable. That oxygen's not going to try to hold that pair of electrons. And so we got either two choices. It can either come back down and kick off a leaving group, or in the case of aldehydes and ketones, it's stuck there until you protonate it. Okay, but that's what's going to happen here. Again, we're going to or that pair of electrons will come back down and kick off our leaving group, giving us our substitution product. So let's just do a specific example here. We have an alkoxide ion, the methoxide ion, reacting with an acyl chloride. So what's going to happen is we're going to have our nucleophile attacking that electrophilic carbonyl carbon, forming the world famous tetrahedral intermediate. And when we get to our tetrahedral intermediate, what do we ask ourselves? Is there a good leaving group? In this case, there is. So that's going to kick off that ion, leaving us our ester. I'm more specific about functional groups, but notice that I very easily converted a more reactive functional group, the acyl chloride, into a less reactive functional group, the ester. This has to be drawn in two steps when we're doing these mechanisms. You have to form that tetrahedral intermediate. This is not a concerted process like a SN2 reaction or anything like that, where you have nucleophilic attack and the loss of the leaving group happen at the same time. Other things to keep in mind, just like we saw last chapter, there are going to be reactions that take place under acidic conditions, and that is sort of code for there should be no negative charges. I just want to say one exception to that are these halide ions, because although they are negatively charged, they are such crappy bases that they can exist under acidic conditions. And likewise, under basic conditions, we'll have these reactions, and that means that you won't see any positive charges. Okay, so just something to keep in mind when we're drawing reaction mechanisms. Okay, so now we have these carboxylic acid derivatives reacting under acidic conditions. What do we think the first step might be? Just like we saw before, the first step is going to be protonation of that carbonyl oxygen, right? So this creates an even better electrophilic carbon because that oxygen's been protonated. And more importantly, or just as important, it also means that when we have nucleophilic attack, the intermediate that's created, our tetrahedral intermediate, oops, I guess this has to have, oh no. Be good and not have any negative charges. Our tetrahedral intermediate that's formed does not have any, that's positive, oh no, it's not, does not have any negative charges in there. All right, so again, a key feature of those acidic mechanisms. Okay, protonation is going to be, protonation of that carbonyl oxygen will be the first step under acidic conditions for our carboxylic acid derivatives, just like it was for aldehydes and ketones. We'll also have reactions that take place under basic conditions. What would have been the first step there? Well, now we're allowed to have negatively charged intermediates. So the first step is simply nucleophilic attack. Okay, so now we have our negatively charged tetrahedral intermediate. That's okay because we're in basic conditions. And lastly, we're also going to see instances where nitrogen is acting as the nucleophile. These are reactions that we said took place under neutral conditions. Just like with aldehydes and ketones, the nitrogen nucleophiles were the only ones where you had to worry about this. Same thing in this chapter, okay? And the big difference here is that you're actually going to have nitrogen's pretty good nucleophile, can attack that electrophilic carbonyl carbon, but importantly, you have both negative and positive charge on that tetrahedral intermediate. So again, this is going to be unique to the nitrogen nucleophile.